Radio for the masses.
Headline edition, July 8, 1947. The Army Air Forces has announced that a flying disc has been found and is now in the possession of the Army.
If the game is rigged, change the game. Game changer.
I occasionally think how quickly our differences worldwide would vanish if we were facing an alien threat from outside this world.
This is Fade to Black with your host, Jimmy Church, on the Game Changer Radio Network.
All right. Well. Look who's back. It's Fade to Black. It is Tuesday, August 6th, 2024. Let's do this. Man, can you tell I'm in a good mood? I'm in a real good mood. Yeah, man. I walked the dark halls last week, but I came out the other side. I did. And so I'll get back to that in a second. We've got a great week on Fade to Black, and so let's go through that right now. Yesterday, there was no show. I was traveling back from Miami. But tonight, Jason Padgett is with us. We're going to be talking about quantum information holography. Now, what? Yeah, we'll get to QIH tonight with Jason. And it's a good thing I'm in a good mood and I've got my brain back, because I'm going to need it all and a really strong cup of coffee for tonight's conversation. We're going to cover all the things that I know and love. Tomorrow night, Paul Smith is with us. One of my favorite people on planet Earth. Paul Smith is with us. We are going to be talking about remote viewing and UFOs. We're going to be doing that tomorrow night with the great Paul Smith. And then Thursday night, Melanie Aguirre is here. And it's so funny. Renee, my speech therapist, wrote me today and said, it's Aguirre. Now, it may be, I've been calling Melanie Aguirre for years, and she's never corrected me. Was she being polite? Right? She just being polite and being cool, or is it Aguirre? I'm going to find out tomorrow. I was going to call Melanie today after I got the email from Renee. Renee is so good. Renee just wants me to be the best that I can be. That's all she wants. She doesn't write me as much as she used to, because I do tongue exercises now all day long because of Renee. She's the absolute very best. So thank you for everybody for sticking with me. And it was a long week for me last week. Now, I do have 3 major events coming up in the second half of 2024, and coming up next in exactly 1 month from today. That is the Contact at Sea cruise to Alaska. That is September 6th through the 13th. Now, I've got some breaking news. I announced this earlier today on this cruise. The ship itself is sold out. Sold out. There's no rooms left. And this morning, the cruise line, gave us 4 extra rooms. One of those rooms may be going to an additional speaker. I thought I was going to have that announced tonight. It's a big name, and we'll have to wait. I just spoke to them before the show. So that's going to be held off until tomorrow. But in the meantime, for the next 7 days, going from here, that special guest that just texted me. So watch this. It's September 6th through the 13th. There you go. You like that? Now, see, you don't know who it was. See, that's the thing. It's that cool. Man, it's good to be me. Love my gig. Anyway, from today, Monday through next Monday, those 3 extra rooms that we have are discounted $500. Okay, so if you want to go on this cruise with me, and I know you do, click on the link below. Use my name. You can use my name. You can use anybody else's name, but you can use my name because you heard it here. $500 off. And you can go to Alaska with me. It's going to be an amazing, life-changing event. We've got an amazing list of speakers. All right, so click on the link below. Save $500 right now. So it's only for the next 7 days. Okay. All right. Next after that is Egypt. That's Forbidden Knowledge with Billy Carson, Elizabeth Carson, and myself. That is October 3rd through the 14th. You can celebrate my birthday with me on October 10th in Luxor in Egypt. Now, that is sold out. But if you sign up and you head down, get on the waiting list. If anything pops up, you can hopefully get on this year's tour. We're already advertising next year for 2025, and you can book that too as well. And then Peru and Bolivia with Brian Forrester, again, sold out for the last 5-6 months. We have a couple of spaces that have opened up there too as well. These 3 tours are 3 paradigm-shifting, life-changing things. All right. Now, Brian Forrester, Peru, Bolivia, that is November 15th through the 27th. Again, the links for that are below. Man, I've got a busy schedule. All I want to do is get to December. That's it. All right. Now, before I bring in Jason, I do want to mention, I posted up on social media today, and I realized that I dropped off the map last week. I wasn't abducted by aliens. The men in black didn't show up at my door. I wasn't interrogated at Guantanamo Bay. I saw the rumors. I got really sick, and I just pushed myself too hard. And I'm pretty healthy. I take all the right stuff. I eat right, and I do all the right things. And you guys know my work schedule. You're with me every night. You see what I do on the weekends. You see the travel that I do and the TV and the film. You see all of that stuff. And yeah, it's work, work, work. And I've pretty much worked 24/7 for the last 12 years. I've had a little time off here and there, but I work. It's my bliss. It's what I do. Well, I did shot for a TV series last weekend. Then I flew out to Indianapolis for my friend Jerry's celebration of life. And right after that, I got sick. And before I flew back to Los Angeles, and it was just like a switch was flipped. And it was weird too. It was like I was normal, and then and it just took over my body really, really fast. And that night, I had to get up at like 4 a.m. for my flight back to Los Angeles. And that night, I went to bed at like 9, feeling really bad. And I couldn't sleep. I was just in body aches and instantly in my throat and headache and bones. And you know what I'm talking about. And I didn't sleep. And then I got up, went to the airport, took the flight back to Los Angeles. Again, didn't sleep, got here to LA, barely made it home. By the time the car dropped me off at my house, I barely made it in the front door. I called Michelle and said, cancel everything for this week. And there was a reason for that, because I had Tuesday, Wednesday, and Thursday to get healthy. Friday, I had to fly to Miami for the Conscious Awards that I'm hosting with Giorgio Tsoukalos. And, you know, of course, Billy and Elizabeth Carson, and there's a lot on that. And I was ill. I was sick. So I took a bunch of meds, drank some NyQuil, and I hadn't slept in like 24 hours. And I passed out on my couch, and I literally slept for 72 hours. Slept through the week. I didn't get a chance to get up and post, put something on social media. This is what's going on. I was out. Man, I was comified. And so that's what happened. I managed to get up Thursday night, pack my bags, and hop on my flight Friday morning, feeling a little bit better. Friday night kind of felt a little bit better. Finally got some sleep. Friday night, Saturday, going through all the events that we had for the awards, things going on all day long. I made it through all of that. Sunday morning, 2 days ago, Sunday morning, I woke up. Whoa, I feel pretty good. So I took the turn, made it, did the award. Nobody knew on the outside. I was cool. On the inside, I was full of question marks, man. I was just like, I'm not going to make it. I'm not going to make it, but I did. And thankfully, coming back yesterday and getting back to LA, I knew that I had taken the turn, and I woke up this morning completely changed. I feel great. So I'm back. Everything's cool. Burned the candle at both ends, snuck up on me, and it got me. It got me good. All right. So that's that. Sorry for the long explanation, but I just disappeared, and I just don't want everybody to freak out. I just passed out for 3 days with the help of NyQuil. All right, let's get to the show tonight. Jason Padgett is with us. Now we're going to be talking about QIH, which is his system, and we're going to go through all of this tonight that he is working on. And how he got there. And we're going to start with that tonight too, as well. I'm not going to do that in the intro because it's such an interesting story, but everything unlocked extraordinary abilities. And I had said this earlier today, and I mean it. He's able to look at math, the universe, and physics in 3D. Now, think about that. We're going to be going through all of that tonight. He ended up writing a book, Struck by Genius, detailing his extraordinary journey. We're going to talk about that. Published in 40 countries, huge international recognition. And, of course, he founded QIH. Now, a screenplay adaptation of his life story is being developed for a major motion picture, and we'll talk about that too as well. His websites are below, and I would like to welcome for the first time to Fade to Black, Jason Padgett. Jason, good evening, young man.
Good evening. How you doing?
Man. Normally I would say not as good as you, but right now I feel pretty dang good.
Yeah, it's nice when you make that turn.
Woo, man. I need it. It's a good thing I did, because with shows like this tonight, I need to always be on my game for every show. But tonight, yeah, right. Really. Tonight I got to be the smartest guy in the room and make it through. But we'll do just that. Now, Jason, before we get started, you get the first time guest disclaimer. Okay. And so let's get that out of the way. The next time you're on the show, you don't get it, but you get it now, which is this. Jason is just you and I sitting on my couch having a conversation as friends. Where the conversation starts, it starts. Where it ends, but we're going to end as friends. You have to accept so we can move forward.
Absolutely.
Oh, man, that's too easy.
Yeah.
Too easy. That was too easy. No questions. No.
I'm okay. I don't get offended if somebody disagrees with me. I'm good with it. All I want to do is explain how this theory works.
Right. Okay. Now, this is where I kind of start with a joke, which is when you read through your work, which I have, and it's extraordinary. It's amazing. But I think to myself, in a cavalier way, I'm not being funny, but I'm being a little bit cocky, where I would say somebody has fallen and bumped their head, right? But in your case, right? In your case. So let's get to that. And then I want to say this one thing. Brian Greene, who I'm a huge fan of, I don't agree with everything. I don't agree with hardly any physicists, but Brian, I think, has a more open mind than most, and I have a lot of respect for him. But he said once during a Q&A about 3 years ago, and I listen to all of his Q&As. They're great. And they're like 3 hours long. And he's just doing these Ask Me Anythings. And he said one night during one of these presentations, I want to frame this pretty close to what he said. He said, I get emails about once a day from somebody that says, I figured it out. I have the theory of everything. And he says, as soon as I read that first line, I delete it. I don't read it. And he said, without doing the kind of that it's impossible for one person to get this done and in a lifetime. Okay. And now I'm a little taken aback by that. There's a lot of physicists out there, well, they have assistants sometimes, but there are a lot of guys out there that were on their own that came up with some pretty extraordinary things that we use to this day. Yeah. When Brian says something like that, does that surprise you in the world of science today where that is their mindset?
It doesn't. I know. I think they're overthinking it. Einstein did what he did in a very, very short period of time all by himself.
That's right.
And I've got advantages of knowing many things that Einstein didn't, having artificial intelligence, which is ramping up the rate that you can do research by thousands of times. So for instance, I can write equations and now have AI go online to CERN and compare my equations predictions to data at CERN and have that done in 10 seconds, whereas that would have taken years before.
Right.
So yeah, one person can get a lot done, and tonight I'm sure we'll discuss that, because I understand though what he's saying about getting those emails. I get those emails all the time. Where
so do I. Believe it or not, I get them too.
Yes. And most of them are just really weird, and they don't make sense. And I understand exactly what he's saying. But every once in a while, there's a gem mixed in with the dirt, and the gunk and the garbage. That's what this is. This is that gem that is mixed in there. And we'll go over what quantum gravity is. And I'm not just going to say it in like a quantum woohoo way. I'm going to give you the equation for it. I'm going to tell you what time dilation is and where it comes from. I'll tell you the black hole information paradox solution, and more. And we'll go into it specifically.
And the audience right now is like, Jimmy's got to be so excited because, I talk about this and I do all the time on the show, and I have physicists on the show and scientists, and we discuss these ideas constantly. I read all the books. I play a physicist on TV, right? And I'm pretty good. Now, even Brian Greene said just recently, I keep going back to him, but I read, he speaks so well.
He's fantastic. I read his books. I love them.
Yeah, they're all great.
Yes.
Even the stuff that he wrote 20 years ago is still pretty strong today.
That's what got me into physics. That's what got me into holography, was reading his books.
Yeah. And now he would have to, if he went back and wrote on the same subject, it probably would be 50% of the original content, because things have moved along so much in those areas. But he said this. He said, if you want to understand the science, you don't necessarily have to know the math. You can understand the concepts if they are explained with confidence by somebody that knows what they're talking about. You can get the books and read them and understand generally what's going on without understanding the math. And that's where I'm at, right? I could hang with a conversation with any physicist. I can, but the algorithms are Greek to me. They're great. Right. I should have been like you. I should have, in 8th grade, I should have had a traumatic brain injury. maybe
what's amazing is that what they're talking about when we talk about algorithms and math, you can take every equation in math and graph it into a shape. So like if you graph negative x squared, it makes this upside down parabolic arc. but the shape is the equation. They're just two ways of looking at the same thing. So people who are good at visualizing things, they're seeing math naturally, and you can graph everything that they're seeing visually into an equation, which is identical in terms of information.
So I took two. I took a physics class and online, right, real deal. And I get to like class number 4, and each one was 3 hours, same as a semester in college, right? A physics class. And so class 1, okay, all right, okay. Man, I'm taking my note. 2, okay, all right. I'm kind of all right. 3, oh man, and I got to 4, and it just got away from me.
Yeah.
It just got away. It's you have to be my brain doesn't work that way. It just doesn't. It doesn't. Yes. It gets lost. All right. Now let's back up. We've kind of laid the foundation here. I'm going to let you tell the story, but you went through a traumatic brain injury. So let's go back to that moment. And then we'll go to where you were in life before that. Okay. But what happened and what did you have to work through?
So when I was younger, I was just a typical kind of goofy boy, goofed off, chased girls, went to bars, and that was about it. And then when I was 32, I got attacked in a robbery and had a brain injury. And I was diagnosed with something called savant syndrome, or acquired savantism. But the main thing that happened is it caused something called motion blindness. And like when you see my hand moving, or anybody, you see my hand moving, it looks like it's moving smoothly. But if you've ever watched a cartoon or like a flip book where you draw pictures on a flip book and then you flip the pages,
right.
It looks like a strobe light. Exactly. So we all see individual picture frames like this, and one part of your brain, its function is to smooth them out so that my hand looks continuous and like it's smoothly moving. That part of my brain was injured. So when things move, I see the picture frames. And in physics, when you're talking about how something is moving, it's called a motion diagram. If something's moving at one speed and you're taking pictures at the same time interval, the distances of the picture frames are the same distance apart. If they get farther apart, it's speeding up. If the picture frames get closer together, it's slowing down. So when you're forced to see in picture frames, you're forced to see in what are called motion diagrams, which they teach us in physics.
And with this type of brain injury, so you were hit in the head or something?
Yeah, I was leaving a karaoke bar. I had a friend, and she was on a first date with this guy, and they had too much to drink, and they called me and wanted to get a ride home. So I went down to this little karaoke bar that they were at. I wound up singing a song. I had a Coke, and we left. And as we left, there was these 2 guys that were singing karaoke in there also. And they walked out behind us, and they just attacked me from behind. Didn't say anything. They just smashed me on the back of the head. I saw this white puff of light, like somebody took a picture. And I found out from a neurologist, that's your brain bouncing off of the inside of your skull when you have a concussion. And I was unconscious from like standing to sitting. And when I came back to consciousness, I didn't know where I was. The world was spinning. I was getting punched and kicked. And I remember having that fight or flight instinct come on. And I remember thinking, I just want to hurt one of these guys before I die. Because I didn't know why I was being attacked or even how many people I was being attacked with. And I remember grabbing the guy's leg and trying to bite him on the leg just to cause damage. But he had these big baggy pants on, and all I got was fabric, and I cracked my front teeth because I tried to bite him so hard. And then
good on you. At least you got one good crunch in.
Yeah. And then I did eventually catch them though, and that's a whole other story. So they eventually grabbed my jacket and ran away. And since they called an ambulance, and while they were there or on their way, I said, wait a second, those guys were singing karaoke. Their fingerprints are on their dishes, which are still on the table. And they had to put their names with their karaoke songs when they sang songs. So we've got their fingerprints and their names on the karaoke slips. And so I went back into the bar and told the people there what had happened. And they said, we don't care. If you want those, go look in the garbage cans. And they wouldn't give us any of that. And so anyway, make a long story short, I wound up hiring 15 people from Labor Ready to ring the restaurant because they were protecting these guys, and we didn't know why at the time, with signs that said "Violent crime happens here," and the news came and covered it. And then the restaurant gave me the attackers' first and last names, and it turned out they were 20. They weren't supposed to be in the bar, and they were dating the girls that worked there. So the girls could tell who has cash when you leave, and the boyfriends would mug you when you left. And I wound up showing up at their apartment like 7 days later, and they got arrested and charged with strong arm robbery.
Right on. Okay, so
Yeah.
there's sort of actually there's a few good endings to this.
Yeah.
Okay, so how long was it when you found out that your brain was now working differently?
So the first thing I remember was going home that night from the hospital. They took me to the hospital, which was just right across the street. And they diagnosed me with a concussion and a bleeding kidney. And just gave me a pain medicine shot and sent me home. And I remember on the ride home, everything just looking so weird. But I'm not sure if that was the pain medicine or if it was me already seeing what had happened. But the next day when I got up and I turned on the water and watched water go down a drain, it didn't look smooth anymore. It looked like these little tiny straight tangent lines that were slowly spiraling down the drain. And it was beautiful. It was spooky. It was disorientating. I had like 3 years of vertigo, but it's absolutely amazing to see. It's like watching light waves bounce, or like the sun bounce off water that's rippling. You know, you see those little sparkles of diamonds. That's what it makes everything look like. It makes everything look like it's slightly pixelated and nothing is smooth. Like the universe is a very high resolution video game.
I did DMT last month twice. That's what it sounds like.
I've had so many people write me and say, you got to try DMT.
Yeah,
but I never have.
Which there's some similarities here. We're not going to get into that discussion, but that was one of my, and I haven't talked about this much, but that was one of my revelations, if I had anything, was how the brain is trying to construct this other dimension. And
Yes.
it's very geometric. It's very, I almost said it's very math, but it is. It's very math.
Geometry is math. They're the same thing.
Yeah. It's Fibonacci-ish. It's struggling to do what it's seeing is the best way that I can say it, which is holographic, man.
Yes.
You know, it's not any different. Okay. So seeing and I just want to for the audience, seeing things like that segmented, but it still has a curve, but now you're seeing the breakdown of the curve.
Yes.
You know, almost Fibonacci-ish.
Literally, I can draw a fractal of any shape, and I can draw like a seashell with a bunch of seashells that makes another seashell. Doesn't matter what the shape is. I can draw a fractal of any shape because space-time itself is this lattice structure, and the lattice itself is a fractal. So space-time is composed of something called Planck qubits, which are these little hexagons that makes this honeycomb shape like a beehive,
which is the universe.
Yes.
And
that geometry is information. So contained within the angles is slope, and slope is information. And that's what we can talk about here in a second, is how the universe has 3 spatial dimensions, X, Y, and Z, forward, back, left, right, up, and down, 1 dimension of information. And that is the information contained within the angles of spatial dimensions, and then 1 dimension of time. So according to this theory, the universe has 5 dimensions, and the one that they're not counting is information. And what this shows is information is actually what's fundamental. Information and geometry are the same thing, but information is fundamental, and gravity arises from it. And we can go into that a little bit later.
Okay. Quick question. Can you insert, it's just a thought here, because this is where I'm going, where I've been leading to lately. Could that information dimension be called consciousness? Could it be the same thing?
What this is showing is that consciousness is energy or mass in a form that is able to retain memories and analyze itself. What this theory is showing is that the universe is a holographic projection from black holes, as weird as that sounds, and that the singularity of a black hole is quantumly entangled with what we call the holographic screen or the event horizon of the black hole. The event horizon of the black hole acts like a monitor that you see, only it's very high resolution, and it's made from something called quark gluon plasma, and it's entangled with the singularity. So the singularity and the holographic screen are perfect mirror reflections of each other. So as I'm doing this,
okay.
Yeah.
Now we're getting ahead of ourselves, and we're going to spend a lot of time on what you just described, and I find it extremely compelling. And this approach to it, okay? And I got a video. Let me. I can't play the video, but what I can do is post a link up to it. So if everybody wants to see what the heck we are talking about, well, let me see. Hold on, I might be able to.
Yes. This video makes it very easy to see. Once people see it, it's like, oh, I get it.
Okay, hold on for a second. Let me see if I can pull this video up for everybody. Is it okay if I play it?
Sure, absolutely. There's nothing I want more.
Okay, let me first see if it's possible. Okay, so but if I can play this, everybody, it's worth the watch, and it's short. It's only 2 minutes. I don't know if it will play the audio. Okay, so let me see. That part I don't know. I would have to, I don't know. Okay, everybody, I'm going to play this. This is with audio, and then somebody tell me in the comments if the audio is playing. Okay, so here we go. Okay, we have no audio.
That's all right.
So now let's start it over, and you get to narrate. Jason,
Okay.
You ready?
So right here, this is how showing how space-time is composed of qubits. Those are the qubits. They're Planck qubits, and on those qubits are little vectors of light called quantum state vectors. That is the singularity surrounded by the holographic screen, and how the singularity is a reflection of what is contained on the boundary or the event horizon of a black hole. That black hole, or all black holes, aren't just points in space where nothing can escape from. They are reflections, just like a drop of water. That drop of water reflects the forest upside down within it, like an infinity mirror, just like the singularity is a reflection of the informational content and the geometrical content of the holographic screen of space-time. And so the black holes project what are called quantum state vectors, which are just these little angles of light, that are Hawking radiation from their boundaries. And that Hawking radiation contains information that describes what is going on inside the black hole. So you can understand what's happening in the black hole by looking at the Hawking radiation that leaves its boundary. It allows you to infer the mass, charge, and spin, the properties of the black hole without looking in the black hole, because you're looking at the Hawking radiation that leaves it. The equation that describes it is the reduced Planck constant, angular frequency times the reduced Planck constant equals mass times the speed of light squared. And when you solve that equation, you get angular frequency equals mass times the speed of light squared divided by the reduced Planck constant. What that means is that you can understand the frequency of what's happening. You can understand by looking at the angular frequency, the mass, charge, and spin of the black hole just by looking at the Hawking radiation that leaves it. And that's the solution to the black hole information paradox, which I can go into more later. But basically, it's related to the photoelectric effect that Einstein proved.
Now, okay, so let's stay right there for a second. It's been theorized, and rightly so, that information is always there. Information doesn't go away. But if we take that idea that information doesn't go away and then combine it with the ideas of the spaghettification of anything that enters a black hole, then it seems to me and to others that you can't have it both ways. The information may be there in the Hawking radiation and what's ejected out of the stream on the other side, but it won't be in order. It seems like you would need to decode it, and including the information of our bodies. If we're spaghettified, are we going to get reassembled back into us on the other side, or are we just a string of atoms and information that will never be encoded again?
No, it will be encoded again, and it's encoded every 10 to the 123rd power Big Bang, which is something called the Bekenstein bound. But so yes, the information is preserved. That's one of that's what they call the black hole information paradox, saying that energy and information can never be destroyed. They must be conserved. And so if something goes into a black hole, since the black hole is a region of space where nothing can escape, not even light, that information and that energy is supposedly lost to the universe. This shows for sure that it isn't. And the way that it does it, it has to do with perspective and quantum entanglement. So if you are going into a black hole, imagine it's just you. And so you're floating in space, and now you're crossing the event horizon. From your perspective, yep, you're in the black hole, and now your information is gone from the universe. But from an outside observer, say I'm away from you, in the next galaxy over, whatever, watching you go into the black hole. As you approach the gravitational field of the black hole, you start to accelerate and go faster because of gravity. Relative to me, that makes time dilation happen to you, where you slow down and slow down and slow down until you approach the event horizon and you appear to be frozen and smeared as information across the boundary or the event horizon of the black hole. What it means is that the black hole to something going in the black hole behaves as a black hole, a region of space where nothing can escape the event horizon, not even light. But to an outside observer watching you go in, because of time dilation, it behaves as a white hole, where you slowly approach, but you can never cross the boundary. A white hole is the exact opposite of a black hole, an event horizon where nothing can enter and everything is expelled. And so the information is preserved on the holographic screen to an outside observer. So it's black holes are white holes to outside observers, and to the thing going in the black hole, it's a black hole, but it's just two descriptions and two perspectives on the same phenomenon.
Now, white holes are white hot right now. Right? This is a subject that is being talked about. We waited forever for the first imaging of a black hole, which happened a few years ago. That was a big deal. Still one of the great documentaries ever made was the assembly of that and all the observatories around the world and the amount of information that was synchronized, and they pieced it together. We got it. Boom. Now we're photographing them more often, it's pretty amazing to me.
Yes.
When will we, the conversation is there is maybe as many white holes as there are black holes.
Yes.
That's an infinite number. Right? That's a big number. So
every black hole is a white hole to an outside observer. To an outside observer watching something go into a black hole, it behaves as a white hole because of time dilation. That object can never enter. And so it's perspective. It's just like Einstein's relativity. You can look at one thing and I can see blue, and you can look at it and see red, depending on how fast we're moving in the Doppler effect relative to what we're looking at. But it's two perspectives on the same informational content.
Now, so the question is this. When will we be in an observational position to photograph a white hole, to image one?
So whenever that event horizon picture that they took of the black hole that they took with the recently, the one that you were talking about, the photon sphere is the white hole. I mean, literally, the event horizon of a black hole is a white hole to an outside observer, and it is a black hole to the object going in. And this Leonard Susskind also demonstrated this. He's the chair of physics at Stanford, showing how as you approach the black hole, you to an outside observer become frozen and smeared across the event horizon. And what my theory is showing is that the singularity is entangled with the holographic screen. The holographic screen is the event horizon surrounding the black hole singularity, and that they're reflections of each other. So even though information from your perspective is lost to everybody else in the universe, that information is perfectly preserved on the holographic screen and then emitted back out as Hawking radiation. It's highly scrambled when it is emitted back out, but you can still recover all the information. And that's what when they talk about the conservation of information and energy, that's what they're talking about. It's like if you had this all-powerful mind and you could reconstruct every little velocity component of everything, then you can reconstruct the information. And that's what this is showing, is that yes, we can recover the information, and we can tell you what's going on inside the black hole by looking at the Hawking radiation leaving it. And very specifically, we can show the charge, mass, and spin of the black hole. And what my theory I just published that is showing and actually proving is that the fundamental properties of particles are equivalent and indistinguishable from the fundamental properties of black holes, meaning that all the elements, us, everything, we are equivalent to the information projected from black holes. With these equations, I can or have predicted the fundamental properties of protons, neutrons, electrons, quarks, and gluons, and more. And then with those first principles equations, where we're looking at it from quantum mechanics up, the equations predict the properties of the fundamental particles, and then we've checked that with the observed empirical values at CERN, and they match perfectly. We can also predict the periodic table. Everything has an atomic weight and atomic mass. This unifies the periodic table and shows that every element has a specific angular frequency. And with these angular frequencies, we can predict the nuclear magnetic resonance of every element in the periodic table, and they match the empirical data at CERN. And there's more than that, but now it's not just equations, it's equations that we can, with first principles, predict what particles are, their Compton wavelength, their mass, their spin, relate it to black holes, and then take those predictions, compare them to CERN, and they match.
Now, why is it, and we're going to stay right here on that, right where we are, but you brought up Lenny Susskind.
He's brilliant.
He is.
Yeah.
You know what? And he's a great orator too, as well. He can explain, right, this complicated subject pretty well. And I enjoy, he's one of the best storytellers out there. He's just amazing.
Right.
But when you look and you look at him, and you look at Stephen Hawking, and you look at Kip Thorne, right? Mm-hmm. And even Avi Loeb, who we were talking about earlier. And when it comes to black holes, all of these guys have pretty solid foundations with their interpretation and theories of what's going on, but they're all different.
Yes.
Right? They don't agree. There's a different concepts. And I think part of the problem is that we may never actually resolve it until we go and visit or somehow get a probe to go inside to confirm something one way or another. I'm not far off base here, am I?
It's very interesting to see how it works. I think the problem, what I believe 100% is the problem that they're having, is that they don't understand what black holes actually are. Black holes typically are looked at just this region of space where gravity is so strong, nothing can escape, not even light. What this is showing and predicting, and I believe proving by showing how time dilation works and predicting all the things that it's predicting, is that black holes are like vinyl records of the cosmos. They transform mass back into light and quantum information, and they project that information onto space-time. They're like hard drives, where they encode the properties of everything that has fallen into them, and then project those properties back out onto space-time. So they're transformative engines. Mass turns to light, and light transforms back into mass, but nothing is ever destroyed. It's just an eternal transformation. And what this shows is that when mass goes into a black hole, that mass, as it's forced to the singularity, is fused like in a supernova, where it converts back into light. The singularity is entangled with the holographic screen, and it projects that information. The way that I explain it, that's real easy to visualize, is I say black holes are like the vinyl records of the cosmos. mass goes in, it converts into light, where the light constructively and destructively interferes, and it makes this interference pattern of bumps and grooves that's like a record player. So think of the singularity as just like a record player, but it's made out of light waves, and it's spinning very fast. And Hawking radiation is like the stylus or a needle that's entangled with the singularity and also entangled with the screen. As the singularity spins, the Hawking radiation reads the interference pattern and imprints it geometrically onto the holographic screen. So the geometry of the holographic screen is the same as the information.
I love that. I love that. And the visual representation in that video really helps a lot.
Yes.
And it applies really well. But I have a couple of issues. So
Yep.
let's clear this up. We'll get to gravity in just a second. But the plasma ring that is spinning on the outside of a black hole that is in all of the visual representations, just like we just saw right here. How if black holes have this gravity suction that we're completely terrified of, that it eats stars, right? Right?
Yep.
It's just like, it's a terrifying concept, but yet the plasma stays on the edge,
Yes.
and supports the outside of the black hole, and it's not going through a time dilation. It's not time traveling. It's not going anywhere. It's staying on the boundary. And
it's oscillating on the boundary like waves, like this.
Right.
And it's actually a quark. Go ahead.
So, but what that says to me is that we could go up to that edge and take a peek and not get sucked in. And would we be affected by time or time dilation that close, but staying in the plasma boundary?
So this shows that boundary is composed of something called a quark gluon plasma, which is they created in CERN when they smashed protons together. So
it's spinning. It's spinning at the speed of light.
Very fast. So the singularity is spinning at like 70% the speed of light. And as it is spinning, the informational content, like the record, only it's a record made of light waves and interference patterns, that is read by the Hawking radiation and imprinted on the holographic screen because they're quantumly entangled. So it's not exactly like a needle touching the singularity and touching the screen. The singularity is entangled with the screen, so that when we find a qubit to be in a spin up state on the screen, the qubit in the singularity is a spin down state. They're perfect mirror reflections of each other. It's literally what's called the anti-universe, and that preserves information also, showing that everything in the universe has a perfect mirror reflection. So when I'm doing this, the mirror reflection of me in the singularity is doing the same thing, only it's just a reflection.
Now, is each one of those particles entangled? And that must be a buttload of stuff.
Everything is entangled. This shows that entanglement is gravity. Specifically, it is the rate of change of the entanglement is gravity. So imagine the holographic screen. This part, I'll try not to go too much into the math, but imagine the holographic screen, or is like a hexagon, like a little honeycomb shape that you see in a beehive. And those little hexagons are something called Planck qubits. They're how you encode information with superposition. Hawking radiation is emitted on these qubits, and the angle of the Hawking radiation encodes velocity as a percentage of the speed of light. The equation is Vx equals c times the cosine of theta. Vy, the velocity component in the y direction, is c times the sine of theta. And the angle squared of that gives you the probability amplitude that qubit will be a 0 or a 1. So the cosine squared of the angle, that gives you the probability the qubit's a 0 or spin up, and the sine squared of the angle theta divided by 2, both of them are divided by 2, gives you the probability the qubit's a 1. And the rate of change of that angle, since the angle is velocity, the rate of change as new vectors are emitted is the change in velocity, and change of velocity is literally acceleration. The definition of it. And Einstein proved that acceleration is equivalent to gravity. So this is showing how the rate that these quantum state vectors change is curvature and is gravity. And it's something I can prove it. I can predict the Earth's gravity, the acceleration on Earth relative based on the rate of change of the quantum state vectors. And I have the new, what's called enhanced time dilation equation. Einstein had a time dilation equation, which is 1 over the square root of 1 minus velocity divided by the speed of light squared. My equation is 1 over the square root of 1 minus d theta divided by dt squared. I'll be real quick. What I'm showing is that d theta is the angle of a quantum state vector on a qubit. It defines velocity. So d theta is the v in Einstein's equation. dt in my equation is the qubit axis, which represents the speed of light, which is c in Einstein's equation. So his equation, 1 over the square root of 1 minus v over c squared, is equivalent and indistinguishable from mine, which is 1 over the square root of 1 minus d theta divided by dt squared. They give the same answer, but his gives the answer and doesn't explain the origin. Mine gives the answer and explains the origin as the rate of change, or how fast these little bits of light are spinning on qubits. And it's also it's empirically verifiable. We can predict time dilation for particles with his equation and mine, and it'll give the exact same answer. Only mine shows the quantum mechanical origin of it and the answer instead of just the answer.
Now, if I showed these, and I can, if I showed your equations and Einstein's, we'll put them side by side, because to Avi Loeb or Brian Greene,
yes,
would they go, okay, all right,
probably at first,
I get it, or would they go, dude doesn't know what he's talking about?
It depends. It depends on the person that you're talking to and how they view the world. Because you would think that scientists would take the time to look at things, but some people, because they don't believe this can be done, they dismiss it instantaneously.
100%.
Yeah.
Well, 99%.
Yeah. Yeah. They don't understand what d theta stands for, and they don't know what dt stands for. So they're like, how is this d theta equal to velocity, and how is dt equal to c? But it's something that I can show them in 5 minutes, how the velocity is encoded by the angle of the qubit. C times the cosine of theta literally encodes the velocity in the x direction as a percentage of the speed of light. Vy, which is the velocity in the y component, is just c, the speed of light, times the sine of theta, and that encodes the velocity component in the y direction. And I can prove with it's not even calculus, it's just trig, that that description of d theta using just the speed of light in qubits is equivalent to the velocity in his equation, and that d theta being the qubit axis, which is just 1 Planck length, and it takes light 1 Planck time to travel 1 Planck length, how that dt is just another way of describing the speed of light. And so the two are interchangeable. They just have to take time to look at it, because it's one of those things that, like, 1 plus 3 equals 4 and 2 plus 2 equals 4. Therefore, 1 plus 3 equals 2 plus 2. It's literally the exact same thing. And it's there is no, once it's properly looked at, there won't be a debate. Because there can't be. They are equivalent. The only thing that will be left to debate is not is this an equivalent description, which it is. It's, can we prove that this is really how it is working? But we should be able to. I mean, I have already calculated the probability that this is correct. For CERN to call something a scientific discovery, it has to be accurate within like 6 standard deviations. This is accurate over 20 standard deviations. And quantum mechanics is only, I think, accurate to like 8 to 10 standard deviations. So this can and does predict gravitational fields. It predicts time dilation that is equivalent to Einstein's. I've translated the uncertainty principle into terms that are equivalent, and proven the uncertainty principle has what's called an enhanced uncertainty principle, which has to do with the rate of change of this angle theta. But we can show that these two are the same. And this also demonstrates the origin of the Schrodinger equation. The Schrodinger equation, which is how the universe evolves as probability as a wave function, this shows origin. And its origin is also the orientation of that quantum state vector. The angle of that quantum state vector, the cosine squared of it, gives you the probability that the qubit will be a 0. The sine squared gives you the probability the qubit will be 1. So basically all I'm doing is, like Einstein had something called a vector tensor field. Imagine you put a piece of graph paper over space-time, and there's just these little grids. And on each little grid in Einstein's equations, there's an arrow. And the direction that those arrows face is describing gravity or curvature at that point. All I'm really doing is saying, hey, Einstein's totally right, but we can enhance Einstein's vector tensor field into a quantum state vector tensor field. If these are quantum state vectors, then they encode probability in addition to curvature. So we can encode velocity components, which is dynamics. Their rate of change is acceleration. Einstein proved acceleration is equivalent to gravity. And we can incorporate probability into the curvature of space-time with these probability amplitudes. And so I have the equations that prove that the probability amplitudes in my equation are equivalent to the probability amplitudes in quantum mechanics. They're the same thing.
It sounds like, and let's go right there. We're going to hit the break here in just a second, and we can pick this up when we come back. This is called a setup, Jason. We're going to set up for when we return. But it sounds like, and I've looked at your work, and again, I'm not a physicist. I just play one on TV. But I absorb this stuff pretty well. And it would suggest to me, and it's okay for you to laugh, that the idea of bizarro world or a universe that is like ours, but is the opposite, must exist.
This shows for sure it does. Not
Right.
only does it, but this shows for sure our universe, the singularity is a perfect mirror reflection of what is occurring in our universe. But this also
Right.
shows that all possible universes actually happen, that the many worlds theory is correct. All possible versions of reality, which is something called the Bekenstein bound. There's 10 to the 123rd power ways that you can reconfigure the holographic screen to make a new history or a new movie. And then once you have that many big,
that's too big of a number.
well, I'll tell you how that doesn't matter. Yeah, I can tell you in a second how that doesn't matter.
10 to the 123. Do we have a name for that?
The Bekenstein bound.
Oh, yeah, that is so big. Like, if we put that in the concept of like years,
It's massive.
it's massive. You have no idea. Like when 13.8 billion, right? The alleged age of the universe, which I
Yes.
don't agree with at all. But I think time is forever, and there is no 13.8, and that's the origin of time. No. And I like people's explanations of it. They are cute. People that are much smarter than me, but I still don't buy into it. But that being said, 13.8 billion is still a long friggin' time. That's a lot of millions. That's a long time, man. That's a
Yes.
13.8 billion years. That's a long time. But when you have 10 to the 123 and you convert that into years, that makes 13.8 billion smaller than a quark.
Yeah, almost infinitesimal. Yeah, it's not.
Yeah.
The main thing, the main important thing is that it's not infinity, and that's what's important about this. Is this shows is that like for this show, like a real theory of everything, you can apply it to everything, and this includes like, is there reincarnation? Are you born again? All these weird kind of questions that people have, but they're real questions. And what this shows is that the universe has a big bang and a big crunch, and a big bang and a big crunch. After 10, because you can only rearrange the holographic screen 10 to the 123rd power different ways, which is huge, but it's not infinity. So after 10 to the 123rd power big bangs, the informational pattern must repeat. And I know that's a huge amount of time, but when your atoms are or when the energy that is you is not in a form that can retain memories, time is meaningless. And so we know this universe is at least, 13.8 billion years old, but I think it is a little bit older than that too. But anyway, just assume that this universe is only 13.8 billion years old since the Big Bang. The energy that is you has been in stars and galaxies and comets the entire time since the Big Bang. Do you remember waiting to be born? You don't.
Well,
it's instantaneous.
No, you don't.
So-
but okay, this is where I said I wasn't going to debate, but I need to get inside of your head for a second. Eventually, I understand this concept that eventually energy's just going to run out. Strong, weak forces, gravity, particles are going to come apart. Everything is going to go. That's it, right? So if we do the Big Bang, Big Crunch thing, when it's coming back in the other, are we suggesting that protons go immortal?
Yeah, this is showing.
You understand what I'm saying, right?
Yeah.
That the gravity forces are going to reset.
This shows that all possible configurations happen, and that everything in the universe is composed of only one thing, and it's light and the information contained within its rate of change. So what makes this confusing, and especially confusing for physicists or quantum mechanics professors, is because they're not studying, and a lot of them don't like hearing this, but it's true. They're not studying base reality. They are studying beautiful things. Quantum mechanics is beautiful. It's studying how the microscopic universe works. Relativity is describing this large gravitational effects, but they're not studying the base reality. And here's how I explain it. So the singularity is in terms of information is equivalent to what's happening on the holographic screen. Think of a holographic screen like a movie or a video game that's very, very high definition and realistic, but think of it as similar. If you're watching a video game and you can see the little avatars on the screen, right? And then you think about the video game that you're playing, but inside the computer, there's zeros and ones that are playing the video game. If I were to print out those zeros and ones inside the computer and hold that piece of paper of zeros and ones next to the monitor, they would look totally different. But informationally, the zeros and ones are what's happening on the monitor. And so what quantum mechanics professors and what physicists are studying is the observable phenomenon that's on the holographic screen. What my theory is showing is that the singularity contains information that is equivalent to both quantum mechanics and relativity, which are only describing what's happening on the holographic screen. And that's why this unifies it, is because, and why they will never unify quantum mechanics and relativity if they're looking at it in terms of just quantum mechanics or relativity, because those aren't describing fundamental reality. Those are describing just the dynamics or just the observable phenomenon on the holographic screen, whereas quantum information holography is showing how we encode an equivalent description to that in terms of information encoded on qubits in superposition.
Okay,
it's wild. We're basically we are the avatars.
I'm with you, and I'm loving it. But if all of this is the way that science wants us to understand, and I'm leaving consciousness aside, this is too much to be natural and by chance. It seems more divine to me. And I'm not going religious.
Yeah, I know it's going.
There must be a smart dude or dudette somewhere with a big ass whiteboard.
Yeah, so what this shows is there is a way to describe how this quantum state vector tensor field forms naturally. But at the same time, I love philosophical questions. That's why I'm into this, is I want to know what happens after you die, where are you going, where you come from, all these things that everybody else wants to know. So a lot of people ask me like about what God is. And what this shows, and like I said, it predicts the particles, fundamental particle properties, and matches the data at CERN. So this is very real. The singularity is the informational content of all possible configurations of our holographic screen, which is the multiverse. It's the Bekenstein bound number, 10 to the 123rd power, different histories that are possible of our universe. And so I ask people, what do you define as God? And most people define God as like the sum total of everything. Well, the sum total of everything is the singularity. It contains all possible configurations of our universe and projects them onto a holographic screen. Another huge piece of empirical data that we've got that shows this is dark energy. So dark energy, this is showing that everything that happens on the holographic screen has a perfect informational reflection of the singularity. So that includes dark energy. So when scientists tried to calculate dark energy from quantum fluctuations, they found that it was like 10 to the 120 to 123 orders of magnitude too large of a value. But what this shows, and think of that number of the Bekenstein bound and that number. So what this shows is all that dark energy at the singularity is all on this one tiny little spot in superposition. If you project all that dark energy onto 10 to the 123rd power versions of our universe, which is the multiverse, and you spread that dark energy out over this vast surface area, it yields the correct energy density that was calculated at CERN. And so
now,
we can
show. Okay. So we've just blown past the break, but we'll get to the break in a second. A couple of things have fallen apart. It started to about 10 years ago. Really started to fall apart about 4 years ago. And I think that the science community is struggling to pull it back together. One, superposition was never verified, right? And that was a big struggle at CERN, and I get that. And then we have string theory and the work that has been going on now for decades, and that the results of string theory may not ever, it's not going to be seen in our lifetime. It's no. And it's maybe with AI, I like your point there. Maybe they can speed things up, but I think that the idea of one elegant equation like E equals MC squared, right? Which is what people are waiting for. That one simplified thing where we can look at that and apply it to everything.
I've got the equation for you.
Well, you know what I'm saying, though, right? To peanut butter or Andromeda, right?
I can tell you the equation right now. The equation is the reduced Planck constant times angular frequency equals mass times the speed of light squared. Reduced Planck constant times angular frequency is the solution, and that equation is how we solve the black hole information paradox by showing that it is a modified version of the photoelectric effect of Einstein, and how these Hawking radiation is this quantized information that is emitted from the boundary of black holes. But with that equation, we can show how angular frequency defines mass, and in fact all things that we see in the universe, including fundamental particles, including gravity, including time dilation. Everything reduces to literally one thing in this theory, and it is the most fundamental thing in the universe, the one thing that is timeless, and that is light and its rate of change. Light compared to itself gives you benchmarks to define velocity, acceleration, and in terms of code, probability. And so the curvature of space-time has information that is encoded in its slope and its rate of change that when it's on qubits, works just like a quantum computer. This shows that the universe is a quantum computer where the bits are these little Planck qubits. It's like the highest resolution hologram possible. If you've ever seen a holographic fan that spins and it makes a little image.
No, it's more simple than that. It's what we are doing right here. You and I are strings of information.
Yes.
What's coming in on, I've got a cable, an Ethernet cable coming in. I've got an encoder. I've got different things, right? I've got all of this. That's digital information transferred to an image. And so we can digest that, and I appreciate that. But let's back up one point, and then we got to get to the break. Yeah. You brought up Lenny Susskind. Now, I'm talking about your equations, okay?
Yep.
You brought up Lenny, and Leonard has got one of the most quotable quotes that I love that will last till the end of time. And his quote is, man, everything that can happen will.
Yes.
It's not going to happen tomorrow, but it might.
Yes.
Eventually, it will. The craziest thought in your mind will happen.
Yes.
And probably a lot. And when you
over
go
and over again
through the vastness of space and time. Now that's crazy. Well, you are saying that your equations do go into all probabilities.
Without question. My equations prove the origin of the sum of histories that Feynman talks about. Feynman diagrams, all these different things that particles can do, and you put them all on top of each other and you average them all out, and that gives you the probability of what's going to happen one moment later.
He did that so well.
Yes, and I can prove the origin of that. The origin of Feynman diagrams are these quantum state vectors. The angle of the quantum state vector encodes probability, but it's just this little tiny qubit that's a Planck qubit. It's super small. But if I look at like a larger object like you, like say I'm looking at Jimmy, if I take you apart into all the little qubits and their little vectors of light on the qubits that describe you, and I sum and I average them all, that gives me the average wave function for you. And if I could see all of the qubits that compose you, I could tell you the probability of how you will behave based on the wave function that is the sum of the history of the quantum state vectors that describe you. And so all we're doing is we're saying his Feynman diagrams are totally correct, but you can break them down into tinier pieces, which are Planck qubits. And those Planck qubits, the average of those little vectors on each qubit, when you take the sum of those histories, they are identical to Richard Feynman's sum over histories equations. And I've also published that on Zenodo. It says it's titled "The Origin of Feynman Diagrams."
Yeah, everybody, we've got links up for Jason. And if you are as dry and as fun as I am, it's great reading, man. Okay, so back to, and then I promise I have to get to a break. I have to pay the bills. But Feynman had a way of visually, and he loved it too, man. He loved it, man. He was a cartoonist, right? And he would do all of his stuff, and people got it. Yeah. And people got it. We need more Feynmans out there too. And he was animated, man. He'd thrown his arms around, and he loved his chalkboards, right?
Yeah.
And where are the Feynmans of today that can help explain these? That they are complex subjects because nobody's explaining them. As soon as you go through a Feynman presentation, and you're like, man, Einstein wasn't shit. I got this, right?
Yeah, I agree. I agree. Feynman could see more than he. And what I love about Feynman and why he is my favorite is I love this quote that he had because I am, like I said, partially classically trained, but mostly self-taught. And I think like Faraday, he was totally self-taught. You need somebody like that to see outside the box. And Richard Feynman had this great quote that I love, which is a lot of these PhDs are confusing their education with intelligence. And I see that all the time. There's a lot of brilliant ones. I'm not bagging on them all, but there's a lot of them that they're what I call information parrots. They're like, did you know that gravity is this much on Earth? Did you know this? But what they're doing is they're just repeating what they heard in a book. What this is showing is that you can describe physics and quantum mechanics in terms of information, and it is the same thing, but you'll never be taught that, at least not yet, in a school book, because they're just following the format that they have and trying to refine it further. But since it's not describing fundamental reality, you can't get past this certain point. You have to describe quantum mechanics and relativity in terms of something different, and that is information. Information allows us to construct four-dimensional objects like a Klein bottle or a Mobius strip. Mobius strip are like this infinite, you can't construct that because in 3 dimensions, but you can construct one in 4 dimensions when you use the information dimension and nothing intersects. And
that's right. And taking it one step further, and I don't want to kick a dead horse here, but when you go back to the Feynmans and the Bohrs and the Wheelers and the Schrodingers and these cats that didn't have computer simulations, 3D modeling, computational aids, and all of that. Those guys, all of them, and they fought like cats and dogs. They stabbed each other in the back. They would get in these circles and debate. Leonard Susskind and Stephen Hawking, some of the best black hole debates ever, done sitting face to face and discussing this. Right? This is no joke.
Yes.
But these guys were thinking about this. Einstein and lensing, right? Think about that for a second. And now he pulled some old work off the shelf that wasn't his, but he looked at the equations and he thought about it. And wait a minute, light, you can see something behind a mass in space, that the light will bend around the mass and you can see what is behind it. That's in his head, man. And he worked the equations out. And that's the whole trippy thing about, and now with all of
exactly how I see it.
But with all the technology today that we have, CERN, right? Fermi labs, we have particle accelerators on every continent. We've got amazing supercomputers, and I think we've kind of slowed down with that. We've lost the creativity input.
That's exactly what I think. And people's careers depend on just trying to be like everybody else and say things that are conform to everything else. For me, it doesn't matter. I'm in this because I love it. I'm in this because I want to know the real truth, but I want to prove it. I don't want to just talk about something that doesn't exist. I want to prove it. But I'm not concerned if I'm wrong about something, then okay, I'm wrong, but it's not going to destroy my career. We're just fine no matter what happens. And but a lot of these physicists, they're too scared to say anything that's out of the norm. But this isn't just different from what they say. This is something, it's provable. I mean, they just need to look at it. The more people that look at it, the more they will confirm it. But it requires them actually looking at it in depth, because a lot of these guys, like I said, they're a PhD in whatever their field is, and they look at this or they hear about it for 1 or 2 minutes and then dismiss it. Well, you're not going to learn how the universe works in 1 to 2 minutes. This took me, 10 years to 15 years, slowly progressing step to step. And only in the past 18 months did it really just explode. And so it's something that they need to listen to. They need to take the time to actually look at it. And many of them don't, which I always say, that's not very scientific of you. So I would like to very politely and respectfully challenge them to look at this. I want critical feedback. I want peer review and desire it more than nothing else, because I know that peer review and that critical feedback will be confirmed, because it does predict what I say it does. As wild as it sounds, I can predict quantum gravity. I do have the solution for the black hole information paradox, the origin of Feynman equations, and more. Because once you understand what a black hole is, all of these questions aren't so hard to answer anymore. But they're all looking at black holes as just this region of space where nothing can escape, not even light. But what black holes are is I call them light drives. They store information and project and conserve that information and project it back out onto the holographic screen.
Now, what about pre-published sites like Archive?
So that's another problem. So with people like me, since I'm not associated with a university, I have tried to publish on Archive, that you can't publish unless you're associated with somebody else who has published a certain amount of articles there, et cetera, et cetera. So I post on a site called Zenodo, which is run by CERN, but it's for people that aren't affiliated, or anybody, but you can also post if you're not affiliated. So I would love for that's one of the reasons why I'm talking about this so much publicly, is I want physicists and professionals, especially informatics professors, the guys who programs quantum computers, they're the ones that are going to get this faster than physicists, because they're thinking in terms of information. But,
well, they also think in terms of science fiction, and they're okay with that.
Yeah.
No, I'm being serious.
Yeah.
I'm not joking about this.
Yeah, science fiction is actually science fact. According to this, everything that you can imagine happens. So any movie that you see on TV is a configuration that the holographic screen can take. There is no such thing as fiction. Every possible thing that you can imagine actually does happen on the holographic screen, which is 10 to the 123rd power number of history. This is how I tell people. I say, think of the, how Netflix has a library of movies, and then it streams those movies to your monitor or your screen. The singularity is like it's like the ultimate streaming service. The singularity contains the Bekenstein-bound number of histories, all possible configurations of our universe. It streams them through quantum entanglement and Hawking radiation to the holographic screen. So black holes are literally like the ultimate Netflix. They contain all versions of history and stream that to the holographic screen eternally.
Well, the idea, just the idea of how a quantum computer works is bullshit. That's science fiction. That is what that's the Marvel universe. That is what crazy people wrote about and doing Batman cartoons, right? I'm not kidding about this.
No, I know. What I tell them,
let me finish real quick, Jason. I want your comment on this, because just the idea, the first lines of how a quantum computer works and what a qubit is science fiction. That it is an entangled particle in another dimension out there to the infinite in both directions. We don't know how it works, but it does. And so we've got a 1, a 0, and an other that's operating in the multiverse out there somewhere. And it's like, wait a minute, what? Now, we would have been called crazy by suggesting something like that's Star Trek. That's Star Trek 1969. But that's where we are today. Yes. And that's why we've got to think outside the box. And that's why the whole qubit thing and what you bring up here is just as valid as anything else.
Absolutely. What I tell them is we have empirical evidence for it now. We have the first empirical evidence that the multiverse exists. And that empirical evidence is that none of them can describe why dark energy's density is what it is. I can. And it does predict the proper energy density for dark energy. But the only way that you can get the proper energy density of dark energy is to say, just like Leonard Susskind, there's an equivalent description of the bulk and the boundary, what's happening in the black hole and what's happening on the boundary or the holographic screen. All the dark energy is at the singularity, but it's way too much when they calculate it. But the reason why it was wrong, or why they didn't understand it, is because they were spreading that dark energy out over all the surface area of our observable universe. But when you calculate that dark energy and you spread it out over the Bekenstein bound, all possible configurations of our universe, it yields the proper energy density of dark energy that they measured. And no other theory does this. And the only way that it works is that if you spread that energy out over all possible configurations, and the fact that it matches dark energy's observed or measured density is something they can't do. And that is real empirical evidence that the multiverse exists, including Richard Feynman's Sum of Histories.
Did you read? Yes, actually, yes. Mm-hmm. Don't get me off on that tangent, because I'll go right there. Did you read the paper? It was released about a month ago. I thought it was going to cause a huge ripple in the scientific community, but the paper was released. I reported on it, that said this. Now, this is published. Okay. That you don't need gravity to create mass. Therefore, dark energy doesn't exist, and we don't know what forces are expanding the universe. Did you read that?
No, I didn't. But I know where mass comes from.
But that flips everything over. That's erasing the entire whiteboard. That's going back to like starting over status.
I don't
in the world of physics.
Yeah, so I know where mass comes from. I know this. Again, everything I say is going to sound unbelievable to most people, especially the physicists watching this. But I'll explain exactly how it works. So Wheeler.
Okay. Let's take our break.
Let's go to the break first.
When we come back, we'll all find out where mass comes from. Okay. This is Fade to Black. Our guest tonight, Jason Padgett. Perfect show. We'll be right back. Stay with us. Subscribe to our YouTube channel to get your alerts and access to over 2,000 videos. Click that subscribe button right now. Go to jimmychurchradio.com and get the Fade to Black official podcast. 2,000 episodes, all of them commercial free for just $2 a month. Hi, this is Jimmy Church of Fade to Black, and I want to invite you to come to Alaska with me on the Contact at Sea cruise. It is this September 6th through the 13th, 2024. We are on the largest ship in the Pacific Ocean. That's right, the Ovation of the Seas. It's an amazing cruise, and a ship this big is so much fun. We've got lots of activities and lots of great speakers. We are leaving from Seattle to Sitka, Alaska, Skagway, Juneau. We're going to end the cruise in Victoria, BC, and arrive in Seattle on September 13th. We've got a lot of amazing speakers, including we've got Seth Shostak, Scott Walter, Stephen Bassett, Daniel Sheehan, Daryl Sims, Mas Adi, Vivian Chavez, Grant Cameron, Geraldine Orozco, Misha Johnston, and Melanie Aguirre, and a whole lot more. All you have to do is go to divinetravels.com. You can also go to contactatsea.com. Both are going to take you to a full event schedule. You can check in, look at the boat, get things ready to go, and maybe get a cabin with a balcony. That's what I'm talking about. Come see the whales. Come check it all out. Let's go to Alaska this September 6th through the 13th, 2024 with me, Jimmy Church. Now, when you head to divinetravels.com or contactatsea.com and get signed up, you know what? Use my name, Jimmy Church. I'll see you there September 6th through the 13th, 2024. Let's go to Alaska. This is Jimmy Church. Please visit and explore Egypt this October 3rd through the 14th, 2024 with Billy, Elizabeth, myself, and very special guest and the #1 podcaster in the world, Sean Kelly. It's simple to do. Just go to forbiddenknowledge.com and click on upcoming tours, or click on the link below. We'll see you there. Watch Into the Vortex on Gaia TV. It's Fade to Black for the screen. Simple to do. Go to Gaia.com, search Jimmy Church, or click on the link below. Follow Fade to Black on Twitter at JChurchRadio. Get all of the show updates every single day. It's now called X, but who cares? How you doing? Jimmy Church here. Special announcement. Get your Fade to Black t-shirts. That's right. Help support the show. Help support everything that we do over here. We've got 2 t-shirts. We've got 2 ways to get them. Get your Fade to Black t-shirt today. Go Backley Tappy. Go to jimmychurchradio.com and become a Fadernaut. Get a membership. That's right. Everything is commercial free. You have access to downloads, and you get to call yourself a Fadernaut. River Moon Coffee, makers of the Fade to Black blend. Truly the best coffee on planet Earth. Just visit rivermoonwellness.com or their Amazon store. It's all simple to do. You can check out the Fade to Black blend, the Game Changer blend, or any of their Black Moon Wellness products. It's the only coffee I drink. It is the best, and it's Doc. Again, rivermoonwellness.com. All right. Welcome back, Fade to Black. I am your host, Jimmy Church. A couple of quick notes I want to throw out to everybody. Number one, I hung out with Sean Kelly this weekend, and you may not know this. Dude is 6'8", like maybe 6'10". I've no exaggeration. He is the same height as Brad Olson, standing next to each other. Brad, I used to always say he's 7 foot tall, and he wants to argue that point. But Sean Kelly is the same height. I'm talking to him. Hey, Sean. Yeah, it's good to meet you, man. Wow. What's the weather like up there? Man, huge. It's trippy. Okay, number two, really quick. The Bentley giveaway is going to happen in December. So go and get registered over at forbiddenknowledge.com and get in the mix, man. I would love for one of the Fadernauts to win the Bentley. And now also a quick little side note. I mentioned this earlier today, and I'm going to just say this really quickly. We gave away a Mercedes at the awards this weekend, and Brad Olson won it. So anyway, so he comes up on stage, and a lady stood up and said, "No, I won it." And so Billy, he comes up on stage. I'm standing right there and watching what's going on, and Billy's looking at the two, and sure enough, and Billy, I'm watching him sweat. He leans into the microphone. This is what kind of guy Billy is. Billy goes, "I'm buying a second Mercedes." He gave away 2 Mercedes at the award ceremony. It was absolutely incredible. Anyway, get over to Forbidden Knowledge, get registered, and get in on that Bentley giveaway. All right, our guest tonight, Jason Padgett. And right before the break, Jason said he knows where mass comes from. Okay, bold. That's big. That's big. Okay, yep. Go ahead. I got to hear.
Okay, so John Wheeler showed that if you can get light to interfere with itself head on, it will constructively interfere and can give rise to mass. What this is showing is that space-time being composed of qubits, which is Hawking radiation emitted onto these qubits, how fast these qubits spin, these vectors create destructive and destructive interference with each other. Where they constructively interfere is just like the Wheeler effect, or it is the Wheeler effect, where the interference patterns of light waves hitting each other head on transforms the light into mass. Because remember, light transforms to mass transforms to light, but neither is destroyed. And they just confirmed this and did it for the first time at CERN, and it was confirmed by the Department of Energy last year that they just created the very first small amount of mass from colliding light waves. And so the interference patterns of light waves is what mass is. Mass is literally like tangled up light.
That's heavy.
That's the Wheeler effect.
That's heavy. Tonight in bed, I'm gonna be laying there in the dark going, oh.
Yeah, if anybody who has a chance, look it up. Like the Department of Energy confirmed that they created a small amount of mass from light, and John Wheeler's equations showed that if you can get light somehow to interfere with itself directly, it will give rise to mass. And that's what my equations are showing, is that how these quantum state vectors constructively when something constructively interferes, the two waves amplify. And if a wave peak hits a wave valley, they become nothing. They cancel each other out. This is showing like the origin of the wave function orbitals is where these, like when you look at like where you can find an electron around a hydrogen atom, there's this probability field of finding an electron. This is showing that where the quantum state vectors constructively interfere, that creates a higher probability density. Where a quantum state vector peak hits a valley, they destructively interfere, and there's no probability of finding the electron there. So, and if you map my equations onto the wave functions, they literally give you the exact same shape as the orbitals of electrons, but it's based on interference patterns and how when they constructively interfere, that increases the probability density, and when they destructively interfere, that decreases the probability density.
Now, here's the thing with that. It sounds, again, I'm just going to say divine. And the reason why it sounds like it's intelligence. And the reason for that, it's not coincidence and it's not frigging luck. It can't be. And the idea of, and if you go back to the Big Bang, I want to talk about gravity. This is where we insert the gravity conversation, because any one of the numbers, gravity off by a tick, was stronger or weaker if we go back to the Big Bang, you and I aren't here right now. In fact, everything is off. Everything is off. And so for us to be here right now, all of the numbers, all of the weights, all of everything, all of those gases, all of that was perfect.
Right.
Nothing could waver. No weights, no gravitational force, nothing. Or the universe just simply it's not a big bang, it's a big poof.
Yeah, so what this shows is that all possibilities actually happen. So in some realities, we don't exist. The reason why we find ourselves existing is because, and that it can be described with probabilities, is because the reason why we exist to observe it is because of the probabilities. It's like saying, like the Earth is going around the sun in this Goldilocks zone. If the Earth was past Pluto, life never would have formed to even start talking about the Goldilocks zones. And so we exist because of that. So what this is showing is all probabilities happen. There are numerous versions of reality where we don't exist, and there are versions of reality where all possible configurations exist. And in those universes where we don't exist, we're not there to question it. So in those universes, it would seem the exact opposite is here. It's like it's obvious that evolved to be this way where we don't exist, whereas here the information evolves in a way that we do exist, and we can then talk about it. But really, we're all just projections of the singularity. So when you talk about like the divine, I mean, like the singularity being the informational content of the universe, we are all the projection of the singularity, meaning we are the universe experiencing itself in all possible versions. You and me, we are all, put us all together and we compose the singularity.
So somewhere there's a show going on, same people, but you're the host and I'm the guy with the big brain.
And every single like one hair is gray, one pixel is purple. Every possible configuration happens, and that's how we actually calculate what happens. And so when we calculate like me walking to the door, we don't calculate me walking to the door. We calculate all possible versions of me going to the door and how they interfere and cancel each other out. The one that doesn't get canceled out is what actually happens. But if those realities don't happen, why is what does happen dependent on them? What this shows.
Well, then why doesn't? Okay, so is it possible? Well, everything is possible. Okay, so, and I agree with Lenny, and I agree with you on that one point. So then I would then venture into this zone, which is, how do we know that in the last 13.8 billion years, that other universes or other big bangs didn't occur inside of our observable universe while we were here. It seems that that's a possibility that has to happen and has to happen a lot. And that includes outside of the observable universe. To suggest that this one thing was a singular event is ignorant.
Exactly.
It must happen all the time.
It does.
Some of them may be little, right?
Yep.
Almost started, right? Kind of like a car with a bad carburetor, and you've got to choke it, right?
Yes.
to get it to start. But it also starts a lot too as well. That has to be the case, which means that you're going to tell me that the one thing that no two physicists can agree on is what gravity is. But you're going to tell me that you do know what gravity is, aren't you?
Very specifically, yeah. So what gravity is gravity, and what's really cool is gravity is not fundamental. Gravity emerges from information, and this is how. So remember, space-time is this lattice of qubits.
Not from mass, but from information.
Yes.
Okay.
Yeah.
All right.
For specifically from the rate of change of information, which is curvature. So if you look at the universe and take one little picture, like a flip book, where you're just taking one moment of time and you're taking a picture of this quantum state vector tensor field I'm describing, which is just a lattice of these little hexagon qubits making a honeycomb shape. On each one of those qubits, there's a quantum state vector, which is Hawking radiation emitted from the black hole. The angle of that quantum state vector encodes velocity. C times the cosine of theta encodes the velocity as a percentage of the speed of light in the y direction. C times the sine of theta encodes the velocity in the y direction. And the angle of it also encodes probability. But that just tells you what's called the instantaneous velocity on the qubit and the instantaneous probability. But in order to have gravity, gravity is equivalent to acceleration. And acceleration is the rate of change of velocity. So when we encode velocity on a qubit, one moment later, when a new bit of Hawking radiation is emitted onto that qubit, that gives you the rate of change of velocity, which is acceleration. So you need two picture frames to define acceleration, but you only need one picture frame to describe velocity and probability. So gravity emerges from the rate of change of the information field, which is curvature.
Okay, so but which version of gravity? Or is it both?
This is both. This is quantum gravity that also describes relativistic gravity.
Right, because we have sucking and pulling and pushing.
Yeah, so gravity is the curvature of space-time, and light follows these geodesics, and it follows the curvature of space-time. So like nothing is actually sucking or pulling; it is the curvature of space-time that you follow these geodesic paths in. It's like they always do that demonstration of like a bowling ball on a trampoline where
it's so famous.
It follows the curvature.
And that's always used as the explanation of why Earth is where it is, because it's rolling around that dish at that point, and it's stable there. Well, it's slowing down, like everything will, and eventually will go down the drain, right on the other side, if you want to look at it that way. But then when we go outside of that, because we have Earth, star systems, right? Solar systems. And I think we, in a general sense, understand that concept. But then when you go outside of that, our star system is doing the same thing, influenced by something else in space. So our star system is in that. And then we go out of that, and then we have the Milky Way that is also influenced by that. And then we go outside of that, where gravity seems to be going in the opposite direction, not at a constant rate, but the rate is increasing and forcing the expansion of the universe. And if that's the case, why doesn't the Milky Way spin apart? Why don't
So
stars spit off of the Milky Way? Why don't things fall apart?
right, right.
It's really strange.
Yeah, that has to do with the fine structure constant in my theory. So the fine structure constant is this value that describes, how these forces interact. It's 1/137. And Feynman said it was one of the most mysterious things. And if he could know anything in his life, what he wanted to know what was the meaning of the fine structure constant. And what my theory is showing is that the fine structure constant, the universe is like a quantum computer where it encodes information. And the fine structure constant is an optimization value that allows you to store and retrieve information at an optimal level. And so the fine structure constant being its value is what allows this storage and retrieval of information in this quantum computational process. And without it being that value, you can't store and process information like we do now, and the universe can't exist as it does. So the fine structure constant is an optimizing condition for storage and retrieval of holographic information.
But if we go back to the big crunch, okay, so at the end of everything, and go back to
And this shows what causes the big crunch too, which is wormholes.
But oh man, you got to go there. I've only got 15 minutes left.
I wish I didn't have to, but it is wormholes.
Okay, so but the expansion, which is increasing, and by most accounts, I think it's generally accepted that it is now on the fringes exceeding the speed of light. Okay, so if that's the case, then what is out there we'll never see, we will never know, because we'll never get to it, and it's dropping off the edge, right? We don't see it anymore because of the expansion. There's that, but the energy must be, something's got to feed the increase of force that is pushing things out. It's the energy has to come from somewhere. And that's the part that I don't understand. And then if we turn around and go back to the big crunch, which some still believe that may be the case, then that energy has got to come from somewhere too as well. I know that energy doesn't ever theoretically go away. It will eventually. Yeah,
it's never created or destroyed ever. It only changes form.
But if we go to the 10 to 23 at the end of everything, there will be nothing.
That's what this shows, is that time is circular. It happens over and over again. So the end is the beginning. It's like the snake eating its own tail forever. All possible versions of the universe happen over and over and over. The only question is how often does each history happen? There'll be some histories that are more common than other histories, and some that are less common, but they all happen. And this shows that they actually all happen simultaneously. Because like you and I think. Go ahead. Yeah.
So if that's the case, and I'm looking at the clock, I've got one other important point I want to swing back to. If that is the case, and we go to this time, this scale, which again, it's a big number, everybody. When you look at 10 to 123 and the concept of that, the answer, a trillion? No, it's a trillion. It's got to be, if it's at 123, it's got to be like a trillion.
It's over Google.
It's a trillion to the 113th power, right? It's something, it's an insane number. But getting out that far, then inside of that linear time, multiple universes would then have been created inside of our ever expanding universe at the same time. Right? That's the way it has to be.
Our universe is composed of black holes and small black holes, which compose larger black holes, which compose our universe, which compose the multiverse. But everything is just black holes, and every black hole is a multiverse. So it's very strange. It's very weird, but everything breaks down into black holes, and how all possible versions just don't happen at this scale. They happen at larger scales and smaller scales. Like you think of our universe as being a qubit. Now imagine that you get so big, like what you were saying is like our cosmological light horizon is where a point that we can't see past, where When you look out, mass can't move faster than the speed of light, but empty space can expand.
Allegedly, I'm going to say.
Yeah. So So according
I'm
to this,
arguing that.
Yeah, maybe with quantum entanglement there might be some some loop.
Well, that right there defeats, and I don't want to say Einstein is wrong, but he was correct in 1915.
Yeah, he was wrong about entanglement. He was definitely wrong about entanglement.
Completely wrong.
Yeah,
completely wrong.
And so
now, let's still hold on before we run out of time. I'm going to show you how smart my audience is. I'm going to post this because it comes down to, what about heat death? This is a really, really big deal. And it's not about, and I'm going to ask for your 1 minute take on this. Heat death, it's more like, well, it could be freeze death too as well. It depends on how you want to look at it. That eventually we're going to expand, stars are going to burn out, the universe is going to settle down at one constant measurement of temperature throughout the universe, one that nothing will survive from, and that's heat death. This is something that is talked about a lot now, isn't it? What's your take on that?
Yeah. Well, this shows that all of those configurations happen. We will get to a point where that is what is happening, but that means that there's still not 100% that field stays at that value. So after a vast amount of time, there are these fluctuations in the field that give rise to like order. So what was the beginning of that question? Sorry, I got distracted here. Heat. So what this is showing is that the quantum state vector tensor field can be thought of as thermal black body radiation from black holes, which is just heat. When you look at the temperature of a room, the temperature of a room is the average velocity of all the molecules. So there could be one molecule over here going really fast. It's hot there. Over here, it's a little colder, but the temperature of the room is the average of all of those. If you look at an object, in my theory, it's composed of all these little tiny quantum state vectors. And when you average them just like heat, that gives you the wave function probability of the entire thing that you're looking at. It is literally, the quantum state vector tensor field can be described as a field that we're just describing like the average velocity of all the little constituent pieces, which is just the same thing as we're talking about when we talk about heat.
Now,
so
back to
all these
hole.
values exist. We will get heat death. We will get where everything is frozen. We will get where everything is every possibility between them. But not just will we get there, they're all happening simultaneously. And we experience one at a time that is relative to our position and velocity of what we're looking at. But they all actually, according to this, happen. And now, we have empirical evidence now that we can predict dark energy and gravity and more, much more. But
dark energy may not exist. That's the other. Okay, so anyway, the debate is out on that one, and you would never think, well, like the Big Bang. How could we debate that? How it's so that dogma is so ingrained, right? Yes. That discussion is so taboo. It's heresy. You're not allowed to go there. But anyway, now let's hold on for a second before we run out of time. I got to get your take on this. Kip Thorne, love him. I do. He's great. And the movie Interstellar, he made, he wrote the movie. It was his idea. It eventually got made. But he wanted the science to be solid and what a black hole looks like and its effects and gravity and time dilation and all of that very well represented in the film. Except I had one problem with one part of it. And that was the scene where Matthew McConaughey went with his ship and his robot into the black hole and came out the other side. Okay. And Matthew McConaughey did it outside of his ship and didn't get spaghettified. Right. Now, is that pushing things too far, or do we go back to Leonard Susskind?
Yeah, we go back to Leonard Susskind. This shows that you cross the event horizon and you don't notice anything, but to an outside observer, you become frozen as information on the holographic screen. So the spaghettification thing, I mean, I guess you can kind of think of it that way. The easiest way to picture it is that mass is just tangled up light, like we were talking about the Wheeler effect. It interferes with itself to become mass. Mass transforms back into light when it goes into a black hole and is fused and squished. Because when you, like a fusion bomb, when you confine or you squish mass into a tiny spot, some of it converts back into light and explodes. Here, the singularity is squishing all that mass into a tiny little spot where it converts back into light, which is an information pattern or an interference pattern, which through quantum entanglement is then projected back onto the holographic screen. Black holes are transformative engines, and that's where they transform mass back into quantum information, and that quantum information is emitted as Hawking radiation back onto the qubits of space-time. And the way that we know the information of what's in the black hole is angular frequency equals mass times the speed of light squared divided by the reduced Planck constant. By looking at the angular frequency, we could tell the mass, charge, and spin of what's happening in the black hole by only looking at the Hawking radiation that leaves its boundary. And so that's where they're all.
You're saying Kip Thorne stayed in bounds, and that's possible.
When you say in bounds, would say that repeat it like.
Well, theoretically speaking, to other physicists, he wasn't taking chances with this idea that Matthew McConaughey could jettison his spacecraft and survive a black hole.
Yeah. I mean, according to and this is just perspective. According to people watching him go into the black hole, he is like torn and spread out over the event horizon and frozen. But from his perspective, he crosses the event horizon.
And that's just crazy to me. Okay,
that's exactly. But it's what Leonard Susskind also believes, and to me, it's what it shows. But it's just because they don't understand that black holes just aren't this spot where everything's becomes this infinitely dense point. They transform that energy back into quantum information. But what happens is dependent on who's looking at it. To you, you're in the black hole and you're gone from the universe and you can't come back. But to somebody watching you go in the black hole, you are smeared as quantum information, and the information that is lost to the universe, a perfect reflection of it, is contained on the holographic screen, which preserves the information. So as the information is destroyed, an equivalent description of it is created simultaneously on the holographic screen.
I've got 2 minutes left. Are aliens visiting our advanced extraterrestrial civilizations, ETCs, visiting planet Earth?
This shows the solution to the Fermi paradox. The Fermi paradox is why aren't we seeing aliens everywhere?
Where are they? Yeah, where are they?
So what this shows is that the universe is information. And once we understand that the universe works like a quantum computer, we can encode a quantum computer with the laws of quantum information holography. And to the avatars in that quantum simulation, that universe is just as real as our universe is to us. It's just lower resolution. So once you get to this point where you understand how the universe is information, we can simulate a universe that is indistinguishable and just as real as this one without ever leaving our planet. So we can study and visit the entire universe, the multiverse, from a simulation that is indistinguishable and equivalent to reality from our own planet. So there is no need to have to travel, because you can experience it through a simulation that is equivalent and indistinguishable from the real universe. The other one thing I wanted to, I think that was it. Yeah, I won't go into that. But basically, it's showing that the technological singularity, when they say AI gets to the point where it's as smart as people, can AI become conscious? And what I say is that this theory shows that we are information. The universe is a quantum computer. So we are proof by being conscious that information can be conscious. So we are the technological singularity. And when we create AI that then becomes self-aware, it is the technological singularity within the technological singularity, because we are quantum information and the universe is a quantum computer, and we consider ourselves conscious.
Now, does that scare the crap out of you, or
no,
does it matter?
It's beautiful. To me, it's beautiful. It shows this interconnectedness of everything, that everything reduces to one thing, that we all have more in common than we don't. and that AI is beautiful and terrifying equally, just like everything else. Every one of these equations, we can do 50% of the things can be beautiful, and 50% of the things can be absolutely awful. But they balance each other out over all the sum of all possible histories. All these things balance.
I've been telling everybody, I'm pixels.
Yes,
I'm not wrong.
You're not wrong. Curves don't exist. When you look at a curve on TV, it's made with square pixels. So if you look in close, there's a zigzag around the edge. And you can cut the pixels in half and in half and in half, and the resolution gets better and better and better, but you never get to like I look like I'm curved, but I'm made with rectangle cells. They're just so small relative to us that looks like a curve. Just like if you look at your screen and you see a circle on your screen and you look in close, you see it's made from square pixels. Reality is the same way. It's just the pixels are the Planck length. So they're so incredibly tiny that things appear to be curved, but nothing is curved. We're pixelated just like the screen, just higher resolution.
So tonight, it was a great conversation with the interpolated Jason Padgett.
I enjoyed it.
Thank you so much. Yeah, thank you so much. Perfect conversation. I can't wait to have you back on. I want to let everybody know, fineartamerica.com. The links for that are below. And Jason Padgett .pixels, by the way, .com is below. And you can go and check out all of his work and chase his stuff down. Jason, perfect night on the show, my brother. Thank you so much.
Thank you. I enjoyed it.
You're the best. Jason Padgett, everybody. Oh, I just cut Jason off because I just got also cut off of the network. So with that, I want to thank all of you. And then tomorrow night, does anybody know what's going on tomorrow night on the show? Oh, tomorrow night, Paul Smith is with us. Remote viewing and UFOs. All of that and much more tomorrow night on the show. But for now, all I've got is Go Backley Tappy. Fade to Black is produced by Hilton J. Palm, Renee Newman, and Michelle Freed. Special thanks to Bill, John, Dex, Jessica, Dennis, and Kevin. Webmaster is Drew the Geek. Music by Doug Aldrich. Intro, Space Boy. Fade to Black is produced by KJCR for the Game Changer Network. This broadcast is owned and copyrighted 2024 by Fade to Black and the Game Changer Network, Inc. It cannot be rebroadcast, downloaded, copied, or used anywhere in the known universe without written permission from Fade to Black or the Game Changer Network. I'm your host, Jimmy Church. Go Backley Tappy.